Hello guys and welcome back to my YouTube channel. Today we're going to be talking about mechanisms. Now, you need to understand mechanisms to be able to complete the rest of this course. And that includes being able to understand substitution and elimination reactions. So before I make a video going over substitution and elimination reactions, I have to take you guys through the basics of mechanisms and arrow pushing. So why do I even need to go over a mechanism, right? Well, mechanisms show us a very important thing. They show us the flow of electrons during a reaction. For example, in this reaction that I have depicted, don't panic just yet. In this video, you are going to learn how to complete a mechanism just as this one. And in every single mechanism ever, what you're going to do is you're going to push arrows to represent the flow of those electrons. Here, we've drawn in a few types of arrows. We've drawn in a blue arrow, a purple arrow, a red arrow, and a green arrow. And arrows are drawn in to either break bonds, as we see in the first step, or to make new bonds, as we see in the second step. A new bond is made between the oxygen and the carbon, whereas in the first step, a bond is broken between a carbon and a chlorine. I just mentioned the word arrow, right? If arrows are going to be used to represent how the electrons are moving in a reaction, hence where they're going to show how bonds are broken, how bonds are made, and in between what atoms, we got to know what an arrow looks like, and we got to know where it comes from and where it's going to. So where are the electrons moving? Well, they're moving from an area of electron density, so the tail end. And the tail end is going to be an electron-rich thing. So E minus richness. This could be a lone pair, or it could be a pi bond in most cases. And every arrow will also have a head of an arrow. And this head of the arrow is going to be pointed at something delta plus or cationic. And that is because opposites attract. So what did I just show you here? Well, first things first, every single arrow is going to have both a tail and a head, where the tail is going to come from something that's E minus rich, and it's going to point at something with the head of its arrow that is E minus poor. The tail end shows where the electrons are coming from, and the head points to where they are going. And since in organic chemistry, the currency is electrons, the electrons need to come from an electron-rich thing, as I previously said. So I want you to think as if the electrons were money. And in real life, if you don't have any money, you can't go to the store and buy some gum. Just as in organic chemistry, you can't draw the tail of an arrow from somewhere that does not have electrons. Now, every arrow will belong to one of the three categories that I am going to go over. Case number 1, you could have a lone pair to a bond. Case number 2, you have a bond to a lone pair. And case number 3 is where a bond will become a new bond. So let's go over case number 1. A lone pair becomes a bond. I want you to think of lone pairs as money in your checking account. Money in your checking account is there to be used. It is not locked in a savings account or some retirement fund. You can technically use it at any point to pay for stuff, for example, for rent or for food. So in organic chemistry, you're going to look for atoms with lone pairs. And those lone pairs can be used to attack things. Where we know attacking of something is represented with an arrow, where an arrow has a tail end and a head end. And it goes from an electron-rich area to an electron-poor area. And it starts at either a lone pair or a pi bond. So if we see an atom with a lone pair, for example, this oxygen has 2 lone pairs. Let's make them different colors, green and red. It can use one of these lone pairs to go and attack something that it likes, where electron-rich things like electron-poor things. So if this lone pair, we're thinking of it as an electron-rich thing, it needs to find something that's electron-poor to attack. So the tail end of my arrow, I'm going to draw it going away from this lone pair. I need to draw the head of my arrow pointed at something that's electron poor. Oh, I see a carbon that has a positive charge. Aha, My head of the arrow needs to be pointed at this carbon with the positive charge. So now all I need to do is connect this arrow, the tail end with the head end. And that is my 2-in arrow, where the oxygen used the 2 green electrons to make a new bond with the blue carbon that was initially cationic. So now we have an OC bond. OC bond. OC bond made. A lone pair on O attacked a carbon, and a bond was made. So a lone pair was used to make a bond. Let's highlight it. A lone pair was used to make a bond. Now I hope you noticed that the oxygen in the final product, this oxygen, is now cationic. Let's look at why this happened. It's all about the formal charge. So let's calculate the formal charge of the oxygen in the beginning and in the end, where formal charge is equal to the valence electrons minus the amount of electrons that atom owns. E minus owns. So the valence count for an oxygen, which you find on the periodic table, is 6. Now I'm going to subtract the amount of electrons it owns currently. So this oxygen owns both of the electrons in each lone pair. So 1, 2, 3, 4. And it owns 1 electron in each of the bonds it has. So 1 electron and 1 electron. But you may ask, well, why doesn't it own 2 electrons in each of the bonds? Because a bond is made up of 2 electrons. Yes, it is, but we have to be more specific. What is a bond? Well, a bond is 2 electrons that are shared between 2 atoms, where each atom contributes 1. So the hydrogen technically owns the other electron in each of these bonds. The oxygen only owns the blue electron. So total up all the electrons that it owns. It owns 1, 2, 3, 4, 5, 6 blue electrons. So overall 6 minus 6 is equal to 0. Let's compare this to the product, where formal charge once again equals valence. Oxygen has a valence of 6 valence electrons. Subtract the amount of electrons it owns. Let's do this in green this time. So it owns both of the electrons in that lone pair, so 2, plus 1 electron in each of the OH bonds. So that's 2 more. We have 4 now. But now it has an OC bond, and in that bond it only owns 1 electron. Therefore, total up all the electrons that it only owns 1, 2, 3, 4, 5 green electrons, minus 5. So overall, this will equal plus 1. And we can say that the oxygen lost an electron. It gave it to that carbon that was initially cationic. And I'm referring to what is drawn as the purple electron. So it lost an electron, become cationic. Lose an electron, become cationic. Lec, and then you can say gain an electron, become negative. Lec gen. But here, nobody gained an electron and became negative. We had a carbon gain an electron and become neutral because it was originally cationic to begin with. So it originally was missing 1 electron. Therefore, when the oxygen gave it an electron, the purple electron, it became neutral in the end. So if you really wanted to, you could make up another acronym. That's like start cationic, gain an electron, become neutral. So that is it for our example where a lone pair becomes a bond. Now let's go over what happens when a bond becomes a lone pair. So here we can see, if we label the carbon attached to the chlorine group in blue, we can see that at the beginning of this mechanism, the carbon had 4 bonds and was neutral. At the end of this mechanism, the carbon has 3 bonds and is cationic. Therefore, it would have had to lose an electron. And we can see that the chlorine starts off neutral, and then it becomes anionic. Therefore, it gained an electron, becomes negative. Well, how did this happen? Well, this is the case where a bond is broken and 1 atom gains a lone pair. So let's draw in all the electrons. We'll make the lone pairs that the chlorine initially has green, and we'll make the 2 electrons in the original Cl bond blue. So 2 electrons in that bond, and let's color them blue. In the end, the chlorine has 4 lone pairs. In the beginning, it only has 3. So we can say in the end, well, it's still going to have the original 3 lone pairs then. Let's color them in green. And it must have gained the 2 electrons in the original C-Cl bond. So how did that happen? Well, the 2 electrons would have came from the bond, and they would have ended up on the atom, the chlorine atom, as a lone pair. So a bond becomes a lone pair. And the carbon that originally was bonded to the chlorine group lost an electron that the chlorine took and will become cationic. The tail came from the bond, and the head of the arrow was pointed at the chlorine, where it becomes a lone pair in the end. Now I just want you to hold with me for a second. You may say, well, does this not contradict what I said in the beginning, how electrons are going to move towards delta positive or cationic things? Yes, that's a great question, I would say, which is why this case number 2, usually happens in consequence to an electron-rich thing attacking that carbon that was initially attached to the halogen. Let's look at what this looks like. So for example, let's say you have some carbon attached to a chlorine group. This chlorine group is electronegative. It's pulling electrons towards itself. It's a thief of electrons. That leaves this carbon directly attached to the chlorine in an electron deficit. Let's call it delta plus. And let's say we had some Nu-, so a nucleophilic thing, something that is electron rich. It has electrons that it can use to attack something that it likes, where opposites attract. So negative things like positively charged or delta plus things. So this nucleophile just needs to find something delta plus and it will attack it. So we'd have 2 in, and then we'd have 2 out. We will later refer to this as a substitution reaction, but right now we're just going over the fundamentals, okay? In my next video, I will specifically go over substitution versus elimination reactions, but in this video, I just want you to get the concept. So what happened? Well, the nucleophile will have made a new bond to the carbon group. That is what the arrow represented. It came from a lone pair on the nucleophile, and it attacked the carbon, so that arrow would become a new bond. Whereas these 2 green electrons in the initial carbon-chlorine group, the tail end comes from the bond, and the head end points onto the chlorine atom. Therefore, the chlorine would gain an electron and become negative, and it would leave as what we refer to as a leaving group. So if it had 3 sets of lone pairs in the beginning, it would gain 1 lone pair and would become negative in the end. So in this example, you can see that we actually combined case number 1 and case number 2. A lone pair became a bond, and a bond became a lone pair. And that is it. That is all for case number 2. Now, the final thing I'm going to be going over is when a bond breaks and moves to form a new bond. All right, guys, our final case is where we have a bond that is going to break, and it will become a new bond. In this case, we are usually going to be dealing with pi bonds. So step 1 would be to try to find a pi bond. Here we can see, oh, there's a pi bond. And now every bond is the sharing of 2 electrons between 2 atoms. So this pi bond is also in between 2 carbon groups. This is very important. So let's call this carbon red and carbon baby blue. Now these 2 electrons, let's draw them in green, in the pi bond can either flick out and attack from the blue carbon or the red carbon. And in most cases, these electrons are going to flick out to leave the more stable carbocation. Because if we consider the 2 hypothetical resonance structures we could draw of this initial pi bond, let's just label the right-hand side as an R group, where we have our red carbon and our blue carbon. Let's say we took these 2 green electrons and we flick them up and onto the red carbon. And this is a hypothetical situation, okay? We would get gain electrons become negative, lose electrons become cationic. So the red carbon would gain both those electrons, gain an electron, become negative. And the blue carbon would lose an electron, become cationic. The other thing that could happen, so versus, the 2 green electrons could flick up onto the blue carbon, where we would get the blue carbon becoming negatively charged anionic, gaining an electron, and the red carbon would become cationic. So now we must ask, which carbocation is more stable? Well, carbocation stability increases as you increase the primariness, where primariness refers to how many carbon groups that carbocation is attached to, where this carbon would be called 2' carbocation, and this carbocation would be called a 3' carbocation. Just to be clear here, 2' saying it is referring to its attachment to one carbon group and another carbon group, 2', where the 3' is attached to 1, 2, 3 carbon groups, where these alkyl groups are electron rich, but they're not greedy, so they're donors, and they can help stabilize carbocations. So we would proceed with the option where the double bond flicks up and onto the blue carbon, leaving a 3' carbocation on the red carbon, which is more stable than a 2' carbocation. That is why these 2 electrons in step 1 of our mechanism are going to flick out, and they're going to attack something that it likes, where electrons like delta positive things. This hydrogen would be delta plus because it is attached to a delta minus chlorine group. So the 2 electrons are going to flick out and attack the delta plus H. And then the 2 electrons in the HCl bond are going to leave. So a bond is going to become a lone pair. And the blue carbon will now be attached to a hydrogen. And the chlorine would gain those 2 green electrons and become negatively charged. So now in this example, we combined case number 3 with case number 2. We had a bond become a new bond, and we also had a bond become a lone pair. So we combined case 3, a bond to a bond, with case 2, a bond to a lone pair. And sometimes you can even have all 3 of the cases that we just went over be combined. For example, when you have a base that is negatively charged, attack a hydrogen that is attached to a carbon, we'll highlight this carbon in blue, that is 1 carbon away to a carbon with a leaving group, where X is equal to the leaving group. X is equal to some leaving group. This leaving group could be a chlorine, a bromine, an iodine, some leaving group. We will later refer to these reactions as elimination reactions. But once again, today I am just going over the fundamental concepts of mechanisms. Here, case 1, we'd have a lone pair to a bond, where the lone pair of the base is going to attack that hydrogen, 2 in. Then we'd have case number 3, a bond to a bond, where the 2 electrons in the green H to the blue carbon bond are going to go 2 over and end up in between the blue and the purple carbon. And we're also going to have case number 2, where a bond will become a lone pair, where the 2 electrons in the purple carbon connected to the leaving group are going to be taken by the leaving group and become a lone pair. So what we would get would be B to the H plus blue carbon, single bond to the purple carbon, plus a new bond, or pi bond now, created by case number 3, bond to bond. And we would also have X minus, which was created by case number 2, where a bond turned into a lone pair. So here we have case number 1, a lone pair becomes a bond. We have case number 3, where a bond becomes a new bond. And we have case number 2, like I said previously, where a bond becomes a lone pair. which occurs when the leaving group takes 2 electrons and leaves with them, where it becomes anionic in the end. Like I said, we will later refer to this as an elimination reaction because a pi bond was made and we eliminated a hydrogen and a leaving group, the X group, in the process of doing so. But we're not going to jump to any conclusions just yet because these are just the fundamentals that we are going over. So I hope this makes sense. I want to finish this video by doing a few examples that combine all the ideas that we learned today. For example, if we were given this question, where the question would have asked us to complete the mechanism by drawing in the proper arrows. So first thing you want to do is actually draw out the HCl bond, HCl. Because whenever we have a halogen, remember, we're going to probably use it as a leaving group because halogens are delta minus, therefore they steal electrons from things that they are attached to. So that's going to leave that hydrogen, let's draw the hydrogen in green, in an electron deficit, so a delta plus state. That means it could be attacked by something that's electron rich. So let's look for a lone pair or a pi bond. Ooh, there's a pi bond. So this pi bond flicked out and it attacked that H. Now the last question we got to answer is, okay, well, did it attack from the blue carbon, a part of the initial pi bond? Or did it attack from the red carbon, a part of the initial pi bond? So as I went over in the last example, we have 2 hypothetical situations that could occur when we have a pi bond. The pi bond could either flick up and onto the blue carbon. So the blue carbon would gain an electron, become negative, and the red carbon would lose an electron, become cationic. Or we could have the other case where the electrons would flick up and onto the red carbon, and the red carbon would gain an electron, become negatively charged, and the blue carbon would lose an electron and become cationic. Now we have 2 possibilities, 1 and 2. You got to proceed with the option that leaves the more stable carbocation. And in option number 2, we can see that we have a 3' carbocation, which is more stable than a 2' carbocation due to alkyl donation, as I went over in the previous example. Therefore, that is why the hydrogen will make a new bond to the blue carbon, a part of the initial double bond rather than the red carbon. And in the process, this will cause the red carbon to become cationic. So that's step number 1. And now step number 2, drawing in all of our lone pairs on the chlorine. We can see that in the product, the chlorine makes a new bond to that red carbon. So how does it do that? Well, it would have had to take one of its lone pairs, where the tail end of the arrow would go away from the lone pair, the area of electron density, and the head of the arrow must point at an area that the electrons want to move towards, so a delta plus or a carbocation. So these electrons will go 2 in. And here we will not see a 2 out arrow because the red carbon is already in a deficit of electrons. And those would be all the arrows that you would need to show to complete this mechanism. Let's do another example. Drawing in all of our lone pairs. Here we can see we have a chlorine that is negatively charged. So negatively charged things, since opposites attract, are attracted to delta plus things. So find something that is delta plus. Well, here we have a carbon that is attached to a delta minus bromine group. Therefore, the 2 electrons on this chlorine are going to go 2 in, bada bing. 2 out, where the chlorine took a lone pair and made a bond, which was case number 1. And the bromine took the 2 electrons initially in a bond, so bond, and made them a lone pair. So lone pair, which was case number 2. Once again, this will later be called a substitution reaction, but right now we are just going over the fundamentals. And a really good practice is to always draw in all your lone pairs. At the end, make sure all the lone pairs are drawn in. So we know to be neutral, in the beginning, the bromine would have had 3 lone pairs. So make sure to draw in those 3 lone pairs. That did not change in the product side as well. Same with the chlorine. Would have had those 3 lone pairs. And the lone pair that was initially green, those 2 electrons end up in a bond. And those would be all the arrows that you would need to draw to complete this mechanism. Let's do one final example. All right, step 1, we got to identify some atom that could use a lone pair or a pi bond to attack something else. Oh, we have an O- here attached to an R group. So this oxygen can attack something that is delta plus. So let's go find something that is delta plus. Oh, this carbon's technically delta plus, but they drew in this H, right? Let's look at the products they gave us. Oh, we can see that there's actually a pi bond that was made. So this indicates to me that this hydrogen would have had to be stolen. So these 2 electrons started as a lone pair and they attacked the hydrogen. And then the 2 electrons in the H carbon bond went 2 over, creating the pi bond. And then the chlorine group, the delta minus group, took the 2 electrons in the initial red carbon to the chlorine that were initially in a bond and turned them into a lone pair. So here we have the combination of all 3 cases that we went over today. The combination of case number 1, where we have a lone pair turn into a bond. Let's highlight this case in red. So we have a lone pair on that oxygen, become a bond between the OH group, right there. Second arrow we drew actually falls into category number 3, bond to bond, where the 2 electrons that were initially in the CH bond became 2 electrons in a CC bond. Finally, we have case number 2, which is a bond to a lone pair, which is what we see when a leaving group takes 2 electrons that were initially in a bond. So a bond to a lone pair. That is it. That is all. I hope this video was helpful. Today we went over the basics of arrow pushing, what an arrow looks like. So an arrow always has a tail end and a head end, where the tail end starts at where the electrons are coming from, and the head of the arrow represents where the electrons are going, where electrons always move from an electron-rich area to an electron-poor area. And then we went over 3 cases that we will see when we push arrows, which is a lone pair becomes a bond, or a bond becomes a lone pair, which we saw in case number 2, or in case number 3, where a bond becomes a new bond. I hope this video was helpful. Please make sure to leave a like, comment, save, and or subscribe to my channel if you find my content helpful. In my next video, I will be going over, as highly requested, substitution and elimination reactions. But before I did that, I just wanted to go over mechanisms and arrow pushing before we got into substitution and elimination reactions, because it is very important to actually understand the fundamentals before we get into classifying any type of reaction. Have a good night. Let me know if you have any questions in the comment box down below.